Namaste, and welcome back to JEE Chemistry with Typical Monk. This is Class 26, Organic Chemistry, Part 1. Carbon builds millions of compounds, and to master them, we first need a language. IUPAC nomenclature is that language, a systematic name that spells out the chain, the functional group, and every branch. And once we can name a structure, we can see its hidden twins, isomers that share a formula, yet differ in the skeleton, in position, or even in the way they twist in three-dimensional space. Today, classification, nomenclature, and the whole family of isomers. One idea at a time. Here is what you will master today. First, the classification of organic compounds. Second, IUPAC nomenclature. The root, the suffix, and the prefix. Third, structural isomerism, its 5 types. Fourth, stereoisomerism, geometric and optical. And fifth, chirality, enantiomers, and the ENA system. One idea at a time. Let us set the foundation. Organic chemistry. It is the chemistry of carbon, and it is classified by chains, by rings, and by functional groups. The IUPAC name, a systematic name built from a root, which is the chain length, a suffix, which is the functional group, and prefixes, which are the substituents. Isomers, compounds with the same molecular formula, but a different arrangement. Masterline, the name tells you the structure, and the structure, once drawn, reveals every isomer. Now, look at the picture, how an IUPAC name is built. The parts. An IUPAC name has 3 parts, a prefix, a root word, and a suffix. The root. The root names the longest carbon chain, meth, eth, prop, but, pent, and so on. The suffix. The suffix names the principal functional group, the ending ol for an alcohol, ol for an aldehyde, and 1 for a ketone. The prefix. The prefix is a locant plus the substituents, written in alphabetical order and numbered to give the lowest set of locants. Now, how organic compounds are grouped. By skeleton, open chain, which is aliphatic, closed chain, which is cyclic, and benzene-based, which is aromatic. The functional group. It is the reactive atom or bond that defines the family and all its reactions. Homologous series, a family whose members differ by a CH2 unit and share the same general formula. Priority. When several groups are present, the senior one takes a suffix and the rest become prefixes. Now the 5 kinds of structural isomerism. Chain isomerism. The same formula, but a different carbon skeleton, straight versus branched. Position isomerism. The functional group sits at a different position on the same chain. Functional isomerism. The same formula, but an entirely different functional group, an alcohol versus an ether. Metamerism. Different alkyl groups on either side of a functional group, as in ethers or amines. Tautomerism. A dynamic equilibrium between 2 forms, as in the keto and the enol forms. Now look at the picture, chirality and enantiomers. A chiral center. It is a carbon bonded to 4 different groups, and so it has no plane of symmetry. Enantiomers. They are the molecule and its mirror image, which cannot be superimposed on each other. Optical activity. Enantiomers rotate plane polarized light in opposite directions. A racemic mixture. An equal mix of both enantiomers, and because the rotations cancel, it is optically inactive. Now the wider world of stereoisomerism. The definition. Stereoisomers have the same connectivity but a different arrangement in space. Nomenclature isomerism sees and chants about a double bond which cannot rotate freely. E and Z. The modern rule, it is Z if the higher priority groups are on the same side, and E if they are on opposite sides. Optical isomerism. It comes from a chiral center, and the 2 enantiomers rotate light in opposite directions. Diastereomers. Stereoisomers that are not mirror images of each other. Now, the 1 mark facts. IUPAC. A root, which is the chain, plus a suffix, which is the main group, plus a prefix, which is the substituents, numbered for the lowest locants. Structural. The 5 types: chain, position, functional, metamerism, and tautomerism. Stereo, geometric, which is cis and trans, or E and Z, and optical, which is chiral, giving enantiomers. Now match each term to its meaning. The root word goes to the chain length. A hydrocarbon goes to 4 different groups. Keto and enol go to tautomerism, and E and Z go to geometric isomerism. 4 pairs, each worth memorizing. Now, how many of these statements are correct? Statement 1. A chiral carbon has 4 different groups. Correct. Statement 2. Enantiomers can be superimposed on each other. Wrong, they cannot. That is exactly what makes them enantiomers. Statement 3. The suffix names the principal functional group. Correct. So the answer 2 are correct, statements 1 and 3. The trap is the superimposable enantiomers in statement 2. Now the 2 mistakes that quietly cost marks. The truth, the suffix names the principal functional group, the substituents become the prefixes. The trap, thinking that enantiomers are the same compound, they are non-superimposable mirror images. The second truth, a chiral center needs 4 different groups, all on 1 carbon. The second trap, confusing position isomerism with chain isomerism. Position moves the group, while chain rearranges the skeleton. Now, test yourself. Answer in your head before the reveal. That is how G speed is built. Here we go. Question 1. The IUPAC suffix for a ketone. The ending 1. Question 2. A chiral carbon has how many different groups? 4. Question 3. Keto and enol is which isomerism? Tautomerism. Question 4. Non-superimposable mirror images are enantiomers. And question 5. Z means the higher priority groups are on which side? The same side. Let us gather it all in one breath. Classification: aliphatic, cyclic and aromatic and bifunctional group. IUPAC: a root plus a suffix plus a prefix numbered for the lowest locants. Structural isomers: chain, position, functional, metamerism and tautomerism. Stereo: geometric, which is cis and trans, or E and Z, and optical. Chirality: 4 different groups, enantiomers, and optical activity. Next class, the electronic effects, the inductive effect, resonance, and hyperconjugation. Organic chemistry begins with a language, the IUPAC name, which packs the chain, the group, and every branch into a single word. And once you can name a molecule, its isomers appear, the same formula, yet different skeletons, different positions, or the subtle 3-dimensional twist that makes a molecule and its mirror image refuse to overlap. Learn the naming. Learn the 5 structural and the 2 stereoisomers, and organic chemistry finds its order. Next class, the electronic effects that drive every reaction. Sarah, David, Lisa, and John all began exactly where you are sitting now. One idea at a time, you will crack G. I will see you in the next class.